A single point of light holds a secret older than our planet. This is the Methuselah star, a beacon that has burned since the cosmos was young. By the end of this, you will understand how we date the oldest stars in existence and why one of them seemed to break our universe. We will confront a star whose first measurements suggested it was born before the Big Bang. How can something be older than time itself? We are about to trace the life of a cosmic elder, from a universe of pure fire to its quiet journey around our galaxy. Its story makes the reign of the dinosaurs feel like yesterday and all of human history a fleeting blink. What do you believe is the oldest thing you have ever seen? This ancient traveler has a name, HD 140283, a catalog number that belies its epic story. You can find it in the constellation Libra, a faint point of light requiring a telescope to see. On the surface, it seems unremarkable, a subgiant star a little larger and a little brighter than our own sun. But its composition tells a different tale entirely. Astronomers call it metal poor, a term that has nothing to do with iron or gold, but everything to do with the star's origin. In stellar astronomy, a metal is any element heavier than hydrogen and helium. This star contains almost none of them. Its atmosphere is a pristine, primordial soup of the universe's first ingredients, hydrogen and helium, with only the faintest whisper of anything else. That is the first and perhaps greatest clue to its age. In the earliest chapters of the cosmos, there were no heavy elements. The universe was a vast, empty canvas painted only with hydrogen, a little helium, and a sea of light. Every atom of carbon, oxygen, silicon, and iron that makes up our world, our bodies, and our sun had to be forged later, inside the furious cores of the first generations of stars, which then exploded, scattering these new elements like cosmic seeds. A star born from that enriched material, like our sun, carries the fingerprint of those ancient explosions, but HD 140283 does not. It formed from gas that was almost perfectly pure, uncontaminated by the ashes of earlier stars. This means it must be a member of that very first generation, or so incredibly close to it that it witnessed the dawn of all complex matter. Yet when scientists first measured its age with our best tools, they were met with a result so baffling it threatened to unravel cosmology itself. The calculations suggested this star was older than the estimated age of the universe. A relic of time appeared to have outlasted time's beginning. How could a candle be lit before the match was struck? This is the profound paradox that makes the Methuselah star not just an object of study, but the protagonist in a cosmic detective story where the very rules of reality are called into question. To solve this cosmic riddle, we need a clock that can tick for billions of years. We cannot point a telescope at a star and read a birth certificate. Instead, astronomers act like cosmic detectives, piecing together a star's history from the faint clues it leaves behind. This field is called stellar archaeology, and its primary tool is not a shovel but light itself. Every star tells its story through the light it emits. By capturing that light and splitting it into a rainbow spectrum, scientists can perform a kind of celestial autopsy. This process, spectroscopy, reveals the star's chemical fingerprints, the precise amounts of hydrogen, helium, and those crucial trace metals in its outer layers. But composition is only part of the puzzle. The other vital clues are the star's intrinsic brightness and its surface temperature, which we discern from its color. A hot blue star burns fuel furiously and lives a short, brilliant life. A cooler, redder star is more frugal, glowing for eons. Once astronomers have these three key pieces of data: brightness, temperature, and composition, they turn to sophisticated computer models. These are vast simulations that encode the laws of physics to chart the life cycle of a star. You can think of them as a library of possible stellar biographies. The scientists then search this library for the simulated star that perfectly matches their real-world measurements of HD 140283. They look for the model that has the same temperature, the same brightness, and the same primordial chemical makeup. When they find that match, the model tells them how long a star with those exact properties has been shining. It is a meticulous, indirect method, like determining a tree's age by measuring its height, the thickness of its trunk, and the rings in its wood, all without ever cutting it down. For most stars, this method yields a reliable, if broad, estimate. But for the Methuselah star, when the first calculations were run, the computer's answer was not just a number. It was a paradox. The models pointed to an age that stretched back further than our best estimate for the universe itself. The cosmic clock, it seemed, was broken. The numbers were impossible, a direct contradiction written in starlight. Initial studies, most notably a landmark analysis using data from the Hubble Space Telescope around 2013, calculated the age of HD 140283 at approximately 14.5 billion years. Let that sink in, 14.5 billion. Now compare that to the most sacred number in all of cosmology, the age of the universe itself, derived from the pristine afterglow of the Big Bang known as the cosmic microwave background. That number is 13.8 billion years. The math created a gap of nearly 700 million years. According to these measurements, the Methuselah star was not just ancient, it was an impossibility. It appeared to be older than the universe. This was the ultimate cosmic anachronism, a relic that seemed to have existed before time began. For scientists, this was not just a puzzle, it was a crisis. It suggested that either our methods for dating stars were profoundly flawed, or our entire understanding of the universe's birth and evolution was missing something fundamental. The very foundation of modern cosmology was facing a direct challenge from a single, quiet point of light in the constellation Libra. How do you resolve a paradox where the evidence points to a reality that cannot possibly exist? Skepticism was the first and most crucial reaction in the scientific community. A paradox this profound does not overturn established physics overnight. It sends researchers back to their labs and their equations, searching for the flaw in their own logic. And in science, every measurement comes with a built-in confession of doubt, a concept known as the error bar. Think of it this way. If you use a worn-out tape measure to check the height of a doorway, you might get a reading of 203 centimeters. But you know your tool is not perfect, so you report your finding as 203 centimeters, plus or minus 2 centimeters. The true height is most likely within that range. The same principle applies to dating a star 13 billion light-years away with unimaginable complexity. That initial, shocking age of 14.5 billion years for the Methuselah star was never a single, solid number. It was the center point of a very wide range. The research paper stated the age as 14.5 billion years, plus or minus about 800 million years. That plus or minus is everything. It means the star's true age, according to that specific set of data and models, could have been as high as 15.3 billion years, which is truly impossible, or as low as 13.7 billion years. And 13.7 billion years fits neatly within the universe's age of 13.8 billion. The most sensational headlines latched onto the upper limit, the number that broke cosmology. But the full story, the scientific truth, was always contained within that quiet band of uncertainty. This is not a cover-up or a mistake. It is the fundamental nature of probing the distant cosmos. Our tools, even the most advanced like Hubble, have limits. The models of stellar evolution, while incredibly sophisticated, still rely on our imperfect understanding of processes deep inside a star's heart. Measuring the exact distance to the star, a critical factor in determining its true brightness, introduces another layer of potential error. The paradox emerged not from a failure of science, but from the bold edges of its current capability. It was a signal that our measurements needed more precision, our models needed more refinement. The mystery of the Methuselah star did not call for a new theory of everything, it called for better detective work. So the astronomers did what they always do, they gathered more clues. The solution arrived not with a single revelation, but through a steady march of better data and sharper models. Enter Gaia, a European Space Agency observatory on a mission to map the Milky Way in unprecedented detail. Unlike Hubble, which might observe a star a handful of times, Gaia has been watching HD 140283 and over 1 billion other stars for years, measuring their positions with staggering precision. Its primary gift to this mystery was a vastly improved parallax measurement. Parallax is the apparent shift in a star's position when viewed from opposite sides of Earth's orbit, and it is the gold standard for determining cosmic distances. Think of it as cosmic triangulation. The more precise the shift you can measure, the more accurate your distance calculation becomes. Gaia's data gave us a new, rock-solid distance to the Methuselah star. Why does distance matter so much for age? Because to determine a star's true, intrinsic brightness, a cornerstone of the stellar models, you must first know exactly how far away it is. A dim star could be a faint ember nearby or a brilliant beacon incredibly far off. With Gaia's precise distance, astronomers could finally calculate the star's true luminosity with far less guesswork, tightening that critical error bar. Simultaneously, the models of stellar evolution themselves were undergoing a quiet revolution. Researchers revisited the assumptions baked into the computer simulations. They paid closer attention to the star's specific chemical signature, particularly its oxygen content. While still metal poor overall, the exact ratio of oxygen to iron in the star's atmosphere turned out to be a crucial clue, hinting at different conditions in its primordial birth cloud. More importantly, they refined how the models handled a process called convective mixing. This is the churning motion that brings material from a star's interior up to its surface, like a giant, slow-moving lava lamp. The rate and depth of this mixing profoundly affect how a star burns its fuel, and therefore how long it lives. Earlier models had to estimate this mixing. Newer ones, informed by better physics and the star's own chemical clues, could simulate it more realistically. When the updated distance from Gaia was fed into these refined stellar models, the impossible age began to retreat. The central estimate shifted decisively downward. A major study published in 2021 presented a new answer. The Methuselah star, HD 140283, was not 14.5 billion years old. Its most likely age was now 12.5 billion years, with an uncertainty of only about 700 million years. That places its birth firmly within the lifespan of the universe, around 1 billion years after the Big Bang. The paradox dissolved. The star was not older than time. It was merely one of the very first witnesses to the era when galaxies were first assembling themselves from the primordial dark. This is not a story of scientists being wrong and then right. It is a powerful demonstration of science working exactly as it should, a self-correcting process that thrives on doubt and is driven by ever better observations. The star did not change, but our ability to listen to its story did. So the star's age has settled into a new, stable consensus. The latest and most precise analyzers, weaving together Gaia's razor-sharp distance data with our most sophisticated stellar models, now point to an age of approximately 13.7 billion years. The uncertainty around this number has shrunk dramatically, and its range now sits comfortably within the universe's own timeline of 13.8 billion years. The paradox, that stunning mathematical ghost, has faded away, but do not let that resolution diminish the sheer wonder of what remains. 13.7 billion years is not a compromise, it is a monument. This star is still, without question, one of the absolute oldest objects ever identified in our galaxy. Think of the cosmic calendar, where the entire history of the universe is compressed into a single year. The Big Bang happens at the stroke of midnight on January 1st. On this scale, our Earth forms in early September, dinosaurs rule in late December, and all of recorded human history occupies the last few seconds before midnight on December 31st. The Methuselah star, it was born in the first week of January. Its light first shone when the cosmos was an infant, a mere 100 to 200 million years after the initial fireball. It witnessed the epoch when the first galaxies were just beginning to coalesce from the primordial dark, when the universe was still assembling its fundamental architecture. Its status as a primordial relic is not just secure, it is enhanced. We now know its true place in history with greater confidence than ever before. It is not older than time, but it is as close to the dawn as we are ever likely to get. A silent sentinel that has watched the story of everything unfold from the very first chapters. To stand on Earth today and look up at this faint star is to gaze across an almost unimaginable gulf of time, back to a universe that would be utterly unrecognizable. This is the cosmic dawn, the first few 100 million years after the Big Bang, when the first pinpricks of light began to pierce an endless opaque fog. The cosmos was a fundamentally different place. It was far more compact, and the space between structures was still searingly hot from the initial explosion. The periodic table was a shockingly simple document, listing only 3 elements: hydrogen, helium, and a tiny trace of lithium. Everything that makes our world tangible and complex, the silicon in rocks, the oxygen in our air, the carbon in our bodies, did not yet exist. There were no planets, no asteroids, no dusty nebulas glowing with color. The universe was a vast, dark, and simple sea of primordial gas waiting for a spark. That spark came from the first generation of stars, often called population 3 stars. These were not like our gentle sun. Theorists believe they were colossal behemoths, hundreds of times more massive, burning their pristine hydrogen fuel with a ferocious blue-white intensity. They lived fast and died young, exploding in cataclysmic supernova within just a few million years. But in their spectacular deaths, they performed the universe's first act of alchemy. Within their furious cores and in the violence of their explosions, they forged the first heavy elements: carbon, oxygen, magnesium, iron, and scattered them into the surrounding void. This was the first pollution of a pure universe, and it was the essential seed for everything that would follow. This is where our star, HD 140283, enters the story. It is not a first-generation star itself, but a second-generation star, a child of that first wave of destruction and creation. It formed from a cloud of gas enriched by the ashes of those earliest massive supernovae. The key clue is in its metal pore signature. It has just a whisper of those heavier elements, only about 1/250th the metal content of our Sun. That minuscule amount is the forensic evidence, the chemical fingerprint of a single prior generation. Its birth cloud was not perfectly pure, but it was only lightly dusted with the remains of the very first stars to ever die. Picture a pristine mountain spring with just a few grains of sand swirling in it, sand from a single, distant rock slide. That is the environment that gave birth to this ancient traveler. It ignited from a cloud still cold and dark, a cloud that had witnessed the first great flashes of light in the cosmos, and then began to collapse under its own gravity, with those few scattered heavy elements trapped inside. When it first began to shine, the Milky Way galaxy itself was still a chaotic, swirling cloud in the process of formation. There were no spiral arms, no stable solar systems, just a young star joining a vast and turbulent construction site, one of the earliest building blocks of the galaxy we call home today. Its light is a direct messenger from that epoch of first beginnings. Its atmosphere is a perfect time capsule sealed over 13 billion years ago. When we analyze the light from HD 140283, we are not just measuring a star, we are directly sampling the raw material of the infant Milky Way. This is the power of its chemical fingerprint. The star is classified as extremely metal-poor, but to understand what that truly means, we need to look at the numbers. Astronomers use our Sun as a baseline, defining its abundance of elements heavier than helium as a value of 1. For this ancient star, the measurement of its iron content is staggeringly low, only about 1/250th that of the Sun. That is not just a small difference, it is a chasm. It tells us the cloud this star formed from had been seeded by perhaps only 1 or 2 prior supernova explosions, compared to the rich, well-mixed stellar graveyard that birthed our solar system. But the story gets even more specific when we look at the ratios between elements. It is not just that metals are scarce, it is which ones are present and in what proportions. For instance, the star shows a notable abundance of carbon and oxygen relative to its extremely low iron. This pattern is a crucial clue about the very first stars that died to create its building blocks. Modern supernovae from stars like our Sun produce a predictable mix of elements. The pattern seen in the Methuselah star suggests its parent explosions were different, likely coming from those first-generation, massively gigantic stars. These primordial giants, hundreds of times the mass of our Sun, would have burned and died in unique ways, forging a distinct chemical signature that was then frozen into the next generation of stars. So, by reading this star's composition, we are indirectly reading the last will and testament of stars that vanished over 13 billion years ago, stars whose light we will never see directly. This makes HD 140283 more than an object. It is a living fossil and a fundamental laboratory. For astrophysicists, it is like finding a perfectly preserved scroll from a lost ancient civilization, one that details the ingredients available at the dawn of galactic history. Every other star in our neighborhood, including our Sun, is like a modern book printed with ink made from countless recycled older books. The information is rich, but it is a blended history. This star is that original, singular manuscript. By studying it, we test and refine our models of how the first stars lived and died, how elements were first scattered across the cosmos, and how the earliest structures in our galaxy began to coalesce from a nearly pure soup of hydrogen and helium. Its faint light holds a direct line back to a universe taking its first, tentative steps toward complexity. The Methuselah star is not a solitary wanderer from the dawn of time. It belongs to an exclusive, ghostly population known as ultra-metal-poor stars, the surviving elders of the Milky Way's first days. While HD 140283 is a local and relatively bright example, astronomers have since identified others that are even more primordial, pushing our view closer to the very first starlight. Stars with names like SMSS J03 1300.36, 670839.3, and He 152300901. These are not catchy names, but cosmic serial numbers that mark profound discoveries. SMSS J0313, for instance, holds the current record for the most iron-poor star known. Its iron content is less than 1/10,000,000th that of our Sun. It is so pristine that researchers believe it may have formed from the ashes of a single, first-generation supernova, a direct child of the universe's very first stellar death. Finding such stars is a monumental challenge, a search for a few faint needles in a galaxy of hundreds of billions of haystacks. They are incredibly rare, as most ancient stars died long ago or were consumed in the chaotic building of the galaxy. So how do astronomers conduct this cosmic census? They rely on massive, automated sky surveys. Projects like the Sloan Digital Sky Survey use specialized telescopes to capture the light and spectra of millions of stars every night. Sophisticated algorithms then sift through this colossal river of data, hunting for the telltale chemical fingerprint, the near absence of those heavy element lines in a star's spectrum. It is a process of elimination on an epic scale, isolating a handful of promising candidates from millions of ordinary stars. Once a candidate is flagged, the world's most powerful telescopes, like the Very Large Telescope in Chile or the Keck Observatory in Hawaii, turn their gaze to confirm the find with exquisitely detailed observations. But why is this hunt so important? Why pour so much effort into finding a few more faint, old stars? Because each one is an independent data point, a single pixel in a much larger picture we are trying to develop. Think of it like trying to understand the history of a vast, ancient forest by studying its oldest surviving trees. If you only have one ancient tree, its story might be unique, an outlier shaped by a single lightning strike or a peculiar patch of soil. But if you can find a dozen or 100 scattered across the forest, patterns begin to emerge. You can start to map the conditions of the entire forest in its youth. Each new ultra-metal poor star we discover adds another piece to the puzzle of our galaxy's chemical evolution. By comparing their precise elemental abundances, we can start to reconstruct the nature of those very first supernovae. Did they all explode with the same force? Did they produce different mixes of elements? The answers are written in the atmospheres of these ancient survivors. Furthermore, they serve as critical tests for our stellar evolution models. The Methuselah star's paradox was solved by refining those models. Every new discovery provides another benchmark, another opportunity to stress-test our understanding of physics across billions of years. They are the foundational witnesses to the Milky Way's formation, and by listening to their collective testimony, we are slowly, painstakingly, writing the first chapter of our galaxy's autobiography. The story of this star's true age is also a story of human vision, of building better eyes to see deeper into time. Our first clear look came from an observatory that has become a household name, orbiting high above Earth's blurring atmosphere. The Hubble Space Telescope was instrumental in the initial studies of HD 140283. Its keen vision provided two critical pieces of the puzzle. First, its precise astrometry, the science of measuring celestial positions, helped pin down the star's tiny parallax shift with far greater accuracy than ground-based telescopes could achieve. This gave us a better, though not yet perfect, distance. More importantly, Hubble's powerful spectrographs performed a detailed chemical analysis of the star's light. It was Hubble that precisely measured those trace amounts of oxygen and other elements, providing the rich, high-fidelity spectrum that fed into the first sophisticated age models. Hubble gave us the portrait, but the distance, a cornerstone of the calculation, remained slightly blurred at the edges. That blur would be eliminated by a new kind of surveyor, one designed not to look deeply at a few objects, but to map the entire sky with relentless precision. The European Space Agency's Gaia mission is a revolution in cosmic cartography. Since its launch, Gaia has not taken pretty pictures of nebulae. Instead, it has been meticulously measuring the positions, motions, and brightness of over 1 billion stars in our galaxy repeatedly for years. For a star like our Methuselah star, this repeated observation is transformative. Imagine trying to measure the slight wobble of a distant buoy on a choppy sea with a single glance. Your view is shaky and uncertain. Now imagine watching that buoy every day for a decade, noting its exact position against the fixed background. The wobble, its true parallax motion, becomes crystal clear. Gaia did exactly this by observing HD 140283 over 70 separate times. It calculated its distance with an uncertainty of less than 1%. This was the game-changing data point. The star's true luminosity could now be known with absolute confidence, removing one of the largest sources of error in the aging process. The resolution of the paradox was a triumph of complementary astronomy. Hubble provided the exquisite detail of the star's chemical makeup and physical state, the who and what. Gaia provided the flawless measurement of its distance and motion, the where and how far. When scientists fed Gaia's precise distance into the stellar models already refined with Hubble's chemical data, the impossible age finally crumbled. The two telescopes, one a deep field specialist and the other a grand surveyor, worked in unseen harmony to correct our vision. This is not just a technical footnote, it is a celebration of human ingenuity. We built machines that can peer into the hearts of stars and measure the geometry of the galaxy itself, all to listen to the faint story of a single point of light. The mystery of the Methuselah star was not solved by a lone genius with a new equation, but by the steady, collective advance of our tools, extending our senses across 13 billion light-years to finally hear time's oldest melody clearly. Those stellar models are far more than simple calculators. They are intricate digital laboratories built from the ground up using the fundamental laws of physics that govern the universe. To understand how we date a star, we must step inside this virtual cosmos. At their core, these models solve a set of equations that balance three competing forces throughout a star's entire structure. The crushing force of gravity, constantly trying to pull everything inward, the explosive outward pressure from nuclear fusion in the core, and the intricate process of energy transport as that fusion-born heat fights its way to the surface to shine as light. Imagine constructing a blueprint not just for a skyscraper, but for a dynamic, living fire that must stand for billions of years. The modelers start with a hypothetical cloud of gas of a specific mass and chemical composition. They then apply the laws of physics to simulate every stage of its life. They calculate the rate of nuclear fusion, which depends on the core's temperature, density, and available fuel. They simulate how energy moves outward, whether by the slow, radiant journey of photons or by the churning motion of convection, where massive bubbles of hot gas rise like lava in a planetary-sized lamp. They track the star's gradual gravitational contraction as it ages. Running this simulation, second by virtual second over billions of years, produces a predicted life story. It tells us how the star's brightness, size, and surface temperature will change from its birth to its death. The challenge and the source of remaining uncertainty lies in simulating the messy, turbulent processes we cannot directly see. Convection is a major one, modeling how gas churns inside a star, how deeply these currents penetrate, and how they mix elements from the core to the surface is incredibly complex. Small differences in these assumptions can change a model's predicted lifespan by hundreds of millions of years. Another subtle factor is atomic diffusion, the slow sinking of heavier elements like iron inward under gravity, subtly altering the internal chemistry over eons. For a star as ancient as Methuselah, these tiny effects compounded over 13 billion years add up. The remaining margin of error in its age, now around 700 million years, is not primarily from bad data. Gaia gave us a superb distance. Our telescopes provided a sharp spectrum. The uncertainty now lives almost entirely within the models themselves, in our imperfect ability to simulate every nuance of stellar physics across such an epic timeline. This is the frontier. Each new discovery of an ultra-metal-poor star provides another test case, another opportunity to refine these digital blueprints. We are not just learning about one star, we are stress-testing our understanding of how all stars live and die. This ultimate timeline, the age of the universe itself, is not a guess. It is a number carved into the very fabric of space, readable in the faintest glow that permeates all existence. To understand why the Methuselah star's initial age caused such a stir, we must first understand the unshakable evidence for our cosmic birthday. The cornerstone is the cosmic microwave background radiation. This is not starlight. It is the afterglow of the Big Bang itself, cooled and stretched by 13.8 billion years of expansion into a uniform, faint whisper of microwave radiation that bathes the entire sky. Imagine the flash from a cosmic birth, so immense that its fading glow still reaches us from every direction, the oldest light we can possibly see. Space missions like Planck have mapped this background with exquisite precision. They see not a perfectly smooth sea of radiation, but a pattern of tiny temperature variations, like a fossilized imprint of the universe's infant structure. By analyzing the statistical properties of these patterns, the sizes and distribution of these hot and cold spots, cosmologists can perform a breathtaking calculation. They can determine the universe's composition, its geometry, and crucially, the time that has elapsed since the Big Bang. The answer from Planck's final data is 13.8 billion years, with an astonishingly small uncertainty of just about 40 million years. That is our foundational timeline. The second major line of evidence comes from watching the universe grow. We know the cosmos is expanding because distant galaxies are all moving away from us, their light stretched to redder wavelengths. The rate of this expansion is called the Hubble constant. By measuring how fast galaxies are receding at different distances, astronomers can essentially run the film of the universe backward, tracing all that motion back to a single point of origin. That extrapolation also points to a beginning roughly 13.8 billion years ago. These two independent methods, one reading the universe's baby picture and the other tracking its growth spurt, converge on the same number. This is why that figure is considered one of the most robust in all of science. It is the wall against which all other cosmic ages are measured. When the first calculations for HD 140283 suggested it was older than this wall, it created a profound tension. Either the stellar models were overestimating the star's age, or our cosmological models were underestimating the universe's. Such a conflict is not a failure, it is a catalyst. It forces scientists to scrutinize every assumption in both fields. The resolution, as we saw, came from tightening the stellar models with better data. But the process illuminated a beautiful truth. Our understanding of the cosmos is a living, breathing edifice. It is tested not by thought experiments alone, but by real, ancient objects whose light demands that our theories align with reality. The Methuselah star did not break cosmology. It helped refine it, proving that even our most fundamental clocks can be made to tick with greater precision. That initial paradox was more than a measurement error. It was a genuine crack in our cosmic worldview, however brief. If the Methuselah star had been definitively older than the universe, it would have meant one of two things. Either our stellar clocks were catastrophically broken, or our story of cosmic origins was missing entire chapters. For a thrilling moment, the latter possibility forced scientists to consider radical alternatives to the standard Big Bang model. Could the universe be cycling through endless expansions and contractions, making our Big Bang just the latest in an infinite series? Perhaps time itself flowed differently in that primordial era, or dark energy, the mysterious force accelerating cosmic expansion, was not constant but evolved in strange ways, altering the apparent age of everything. Some theorists even revisited the idea of a steady-state universe, where matter is continuously created to fill the void as space expands, a concept with no definitive beginning at all. These were not fringe ideas, but serious hypotheses explored at the very edges of cosmology, prompted by a single point of conflicting data. The paradox served as a vital stress test. It pushed researchers to ask the hardest questions about their most cherished assumptions. Could the cosmological constant, which represents dark energy's strength, actually change over time? What if the early universe went through a phase of hyper-fast expansion called inflation that was more complex than our simple models suggest? Each alternative was a potential key to a lock that did not, in the end, exist. This is the true engine of scientific progress, not the quiet confirmation of what we already know, but the intense collective scrutiny that occurs when evidence contradicts our fundamental narrative. The resolution, achieved through Gaia's precision and better stellar models, ultimately reinforced the standard model of cosmology. The Big Bang timeline held firm. Yet that period of uncertainty was far from a waste. It proved the resilience of the scientific method, a process that invites its own destruction to emerge stronger. Every exotic theory considered, every model stretched to its limit, deepened our understanding of what the universe is not and sharpened the tools we use to understand what it is. The Methuselah star did not rewrite the textbooks, but it made us read them with a far more critical eye, ensuring that the story we tell about everything is not just compelling, but as close to true as we can possibly make it. Its journey from the dawn of time now points toward a quiet, inevitable conclusion. For over 13 billion years, HD 140283 has been a stable, steady fusion reactor, quietly converting the hydrogen in its core into helium. But that era is ending. Astronomers classify it as a subgiant, a star that has begun to leave the main sequence, the long, stable adult phase of stellar life. The hydrogen fuel at its very center is nearly exhausted. This is the beginning of the end for a star like ours, a process that unfolds over hundreds of millions of years, a slow-motion finale. With less fusion energy pushing outward from the core, the star's delicate balance begins to tip. Gravity, patient and relentless, gains the upper hand. The core will start to contract and heat up under this increased pressure. Meanwhile, the outer layers of the star, responding to the changes deep within, will do the opposite. They will expand dramatically and spectacularly. HD 140283 is destined to become a red giant. It will swell to a colossal size, its outer atmosphere growing cooler and redder as it inflates. If it replaced our Sun, its outer edges would likely engulf the inner planets, perhaps even reaching Earth's orbit. This is not a violent explosion, but a majestic, inevitable swelling. For a time, it will burn brighter than ever before, a brilliant ruby in the Libra constellation, visible even to the naked eye as a striking beacon. But this phase is unstable. The star will pulsate, shedding great gusts of its own atmosphere into space. Eventually, the gravitational struggle will reach a climax. The star will be unable to hold onto its vast, distended outer layers. They will drift away, forming a beautiful, glowing shell of gas illuminated by the star's hot, exposed core. This is a planetary nebula, one of the most beautiful sights in the cosmos, a final, artistic flourish. The nebula will expand and fade over tens of thousands of years, scattering the star's enriched material. The helium and the tiny trace of heavier elements forged in its final days back into the galactic void. And what remains, the core itself now exposed, will be a white-hot, Earth-sized cinder called a white dwarf. This is the star's final form. With no fusion left to sustain it, this incredibly dense remnant, a teaspoon of its material, would weigh as much as an elephant here on Earth, will simply glow with leftover heat for billions upon billions of years, slowly fading from white to yellow to red, and finally to a cold, black lump of crystallized carbon and oxygen, a dark diamond adrift in the silent galaxy. This is a peaceful death. It stands in stark contrast to the fate of the massive, first-generation stars that seeded this one's birth cloud. Those titans lived fast and died young in cataclysmic supernova explosions, blasting the heavy elements that built future generations across the cosmos. Theirs was a story of brilliant, creative violence. The Methuselah star tells a different tale, one of profound endurance and a gentle, almost graceful exit. Its complete biography now spans from a universe of pure fire through the quiet eons of stable light to a final, fading ember. It witnessed the first light, helped build a galaxy, and will end as a cold monument to time itself, long after our own sun has followed a similar path. Its story is a reminder that in the cosmos, even an ending can be a thing of breathtaking beauty, a final contribution to the endless cycle of stellar life and death. This ancient star's quiet journey illuminates a profound truth about our own existence. Its pristine composition, that near absence of heavy elements, means it almost certainly sails through space alone. The cosmic ingredients for rocky worlds like Earth simply were not available in meaningful quantities when it formed. The dust and gas that swirled around it in its youth contained too little silicon, iron, and nickel to clump together into substantial planets. Any orbiting bodies would likely be small, icy worlds, not terrestrial spheres with rich geology and protective atmospheres. For life as we understand it, which is built from a diverse palette of elements and requires a stable, complex planet, the environment around a star like HD 140283 would be a barren desert. This stark reality leads us to a powerful and humbling concept, the cosmic habitable epoch. The universe was not always ready for life. It had to mature, to be chemically enriched by generations of stellar lives and deaths. Think of it as a cosmic kitchen. The Big Bang provided the basic staples, hydrogen and helium. But to bake the complex cake of a living world, you need other ingredients: carbon, nitrogen, oxygen, phosphorus, iron. Those had to be cooked up inside stars and then scattered across the galaxy by supernova and stellar winds. The first stars, those massive population 3 giants, were the initial chefs, producing the first batches of heavy elements in their violent deaths. The second generation, stars like our Methuselah star, incorporated a tiny sprinkle of those new elements, but it was not enough. The galaxy needed more time, more cycles of star birth and death, to stir and mix these cosmic ingredients into the rich, complex soup from which solar systems like ours could eventually form. Our Sun is a latecomer, born roughly 4.6 billion years ago from gas that had been recycled and enriched over nearly 9 billion years of galactic history. That long wait was not a delay, it was a prerequisite. It allowed for the buildup of the exact elements needed to form our rocky planet, to fill our oceans with water, and to provide the chemical diversity that life exploits. We are not just products of our Sun, we are the legacy of countless ancient stars that lived and died before our solar system even existed. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged in stellar furnaces and cataclysmic explosions that occurred over billions of years. The Methuselah star represents the early, sterile chapters of that story. Its light is a beacon from a time before the universe could dream of planets like ours, a reminder that our existence is tied to a specific, fertile moment in cosmic history, made possible only by the patient work of stellar generations long gone. The name we have given this star is a story in itself. We call it the Methuselah star, a nickname drawn from ancient texts that feels perfectly suited to an object of such impossible age. In the Hebrew Bible, Methuselah was a patriarch said to have lived for 969 years, a lifespan that became synonymous with extreme longevity in human culture. To name a star after him is a profound act of translation, bridging the vast gulf between our brief human stories and the epic narratives of the cosmos. It transforms a catalog number, HD 140283, into a character. It makes the abstract tangible, framing this ancient ball of plasma not just as a data point, but as an elder, a witness, a traveler from a forgotten age. This instinct to name and mythologize is not incidental. It is fundamental to how we grapple with concepts that dwarf our everyday experience. A star older than our planet, older than our solar system, older than almost everything we can see, challenges the very framework of human history. Our recorded timeline stretches back mere thousands of years. Our civilizations rise and fall over centuries. To confront an object that has persisted for billions of years is to stare into a kind of temporal sublime, a dizzying perspective that makes our entire species feel like a momentary spark in a long, dark night. This star becomes a cultural touchstone because it embodies our deepest questions about origin and endurance. Where do we come from? What was here before us? What will remain long after we are gone? The Methuselah star does not answer these questions, but it gives them a physical anchor, a real point of light in the sky that we can point to and say, that right there has seen it all. This human connection extends beyond mythology into the stories we tell ourselves about the future. In science fiction, ancient stars like this are rarely just stars. They become destinations, the homes of unimaginably old alien civilizations, or the sites of cosmic archaeology. They are portrayed as waypoints on galactic maps, holding secrets from the time before time. A spaceship might journey to such a star not to find life, but to find ruins, to decipher the messages left by a culture that flourished when the galaxy was young and then vanished without a trace. These narratives reveal a fascinating truth. We project onto these ancient objects our own hopes and fears about memory, legacy, and survival. We imagine that if something can last that long, it must hold meaning, it must be a keeper of secrets. In a very real sense, the scientific study of HD 140283 is a version of that same story. We are the archaeologists and our telescopes are the spaceships, allowing us to remotely excavate its light for clues about the universe's lost youth. The nickname Methuselah, then, is more than a label. It is a bridge. It connects the cold, precise data of spectroscopy and stellar models to the warm, human fascination with time and our place within it. It reminds us that science is not separate from culture, but a continuation of our oldest impulse to look up at the night sky and tell a story about what we see. This star's light may have begun its journey in a universe of pure hydrogen, but by the time it reaches our eyes, it is woven into a tapestry of human wonder, a single thread connecting the cosmic dawn to our endless curiosity. Even for a star that is, in cosmic terms, practically our neighbor, the Methuselah star remains frustratingly faint. At a distance of around 190 light-years, you might expect it to be a prominent jewel in the night sky. Yet it shines at only magnitude 7, far too dim for the unaided human eye to perceive. You would need at least a small telescope to even glimpse it as a faint, unremarkable point in Libra. This presents the first and most fundamental challenge for astronomers. How do you conduct a detailed forensic examination on a subject that offers so little light to examine? The answer lies in a patient, painstaking process of cosmic light gathering. To perform the high-precision spectroscopy needed to read its chemical fingerprints, scientists must collect not just a few photons, but millions of them. This requires pointing the world's largest telescopes, with mirrors 8 or 10 meters across, directly at this single point for hours at a time. A single observation might involve an exposure lasting an entire night, just to accumulate enough of that ancient light to create a spectrum clear enough for analysis. Every photon that arrives after a journey of nearly 2 centuries is precious, and capturing them is like trying to fill a thimble with dew dripped from a leaf, one droplet at a time. For ground-based telescopes, the challenge is compounded by our own atmosphere. The air above us is turbulent, constantly shifting and blurring the light from stars, an effect that makes them twinkle beautifully to our eyes but smears their delicate spectra into uselessness for precise science. It is like trying to read the fine print on a distant sign while looking through a heat haze rising from asphalt. To overcome this, astronomers use a technique called adaptive optics, where a computer analyzes the distorted starlight hundreds of times per second and commands a flexible mirror to warp in the opposite direction, canceling out the atmospheric ripple in real time. It is a breathtaking feat of engineering, but it is not perfect. This is why space telescopes like Hubble were so revolutionary for this work. Positioned above the veil of the atmosphere, they could stare with an unwavering gaze, collecting that faint light with crystal clarity over many orbits. The data that resolved the star's age paradox was built from such marathon observations, a testament to both human ingenuity and immense patience. Each new insight into this ancient traveler is hard-won, a secret pried from the darkness by the most powerful eyes we can build and the relentless will to keep them open, night after night, gathering whispers from the dawn of time. Yet even with a resolved paradox, the conversation is far from over. Science thrives not on final answers, but on the subtle tensions that push our understanding forward. For the Methuselah star, the broad consensus is clear. Its age aligns with the universe's timeline. But if you peer into the finer details of recent research papers, you will find a fascinating undercurrent of debate. Different research teams, using slightly different stellar models or prioritizing different chemical signatures, can still produce age estimates that brush up against the edge of possibility. Some analyses, when they push certain assumptions to their limits, yield a best-fit age of perhaps 14 billion years, a whisper over the cosmological line of 13.8. The crucial point is that these slightly higher figures always, without exception, sit comfortably within the stated margin of error. They are not claims of a broken universe, but illustrations of the remaining uncertainties in our stellar blueprints. The debate now focuses on the most precise values of the star's fundamental parameters. How much convective mixing actually occurs in its interior? What is the exact ratio of oxygen to iron, a number that hints at the specific type of supernova that enriched its birth cloud? Even the accepted rate of the universe's expansion, the Hubble constant, is subject to its own ongoing debate among cosmologists, and that number subtly influences how we interpret everything. So the Methuselah star has transitioned from a crisis to a benchmark. It is no longer an object threatening to overturn cosmology, but a celestial touchstone, a standard against which we test and refine our most precise astrophysical tools. Each new observation, each incremental improvement in our models is measured against this ancient traveler. Does our latest simulation now accurately predict its luminosity? Does our new spectroscopic technique resolve its chemical makeup more clearly? This is how science progresses in the absence of earth-shattering paradoxes, through meticulous collective fine-tuning. The story of HD 140283 is not fully closed, and in a way it never will be. As long as it shines, it will remain part of a continuous conversation, a quiet voice from the dawn of time helping us write the ever more accurate story of everything. Its status as a second-generation star is perhaps its most profound scientific gift. HD 140283 carries within it the ghostly signature of the true cosmic pioneers, stars we have never seen and likely never will. These are the legendary population 3 stars, the universe's very first fusion engines. Picture a cosmos still dark and simple, filled only with vast clouds of pristine hydrogen and helium. Gravity began to pull these clouds together, but without the heavy elements that help modern gas clouds cool and fragment, these first clumps could grow to staggering sizes. Theorists believe population 3 stars were not like the stars we know today. They were likely behemoths, hundreds of times more massive than our Sun. They would have burned with a ferocious blue-white intensity, living brilliant, explosive lives of only a few million years before collapsing in titanic supernova. Their deaths were not an end, but the essential first act of cosmic creation. Within those cataclysmic explosions, the universe forged its first heavy elements, the carbon, oxygen, silicon, and iron that are the building blocks of everything complex, including us. And then they vanished, because they lived so fast and died so young, and because the universe has expanded and evolved for so long. The light from any individual population 3 star is lost to us, stretched into oblivion or drowned out by the glow of billions of younger stars. They are the ghosts at the dawn of time. This is why a star like Methuselah is so invaluable. It is a direct descendant. It formed from a cloud of gas that had been lightly seeded by the ashes of one or more of those first supernova explosions. The extremely low, but not zero, metal content in its atmosphere is the forensic evidence. It is the chemical fingerprint of a single prior generation. By studying the specific pattern of elements in HD 140283, the exact ratios of carbon to iron or oxygen to magnesium, astronomers can perform a kind of cosmic archaeology. They are reverse engineering the properties of the long-dead star that polluted its birth cloud. Was it a single, colossal supernova, or did material from several explosions mix together? The elemental clues hint at the mass and explosion energy of those first stars. In this way, the faint light from this ancient subgiant becomes our only window into the era of the true cosmic pioneers. We are using a surviving witness to investigate a crime scene that vanished over 13 billion years ago, piecing together the nature of the first architects of our chemical universe. Its orbit through the galaxy is a final, silent testament to its ancient origin. While our Sun sails smoothly within the crowded, flat plane of the Milky Way's disk, the Methuselah star follows a very different path. It belongs to the galactic halo, a vast spherical cloud of ancient stars that envelops the entire disk like a ghostly, cosmic cocoon. This halo is the galaxy's archaeological record, populated almost exclusively by stars that formed in the Milky Way's chaotic infancy. HD 140283 moves on a long, elliptical, and highly inclined orbit. Picture a vast, tilted oval with the star itself as a solitary traveler. It spends most of its time soaring high above the dense, starry plane of the galaxy, then plunges down through it, only to swing out again into the lonely depths of the halo. This is not a quick commute. A single orbit likely takes hundreds of millions of years. For much of its journey, it looks down upon the brilliant spiral arms from a great height, a silent observer to the ongoing drama of stellar birth and death in the bustling disk below. This kinematic signature, its motion, is as much a marker of its age as its chemical fingerprint. In the early galaxy, before it had settled into its orderly, rotating disk, stars formed in chaotic, collapsing clouds that gave them random, plunging orbits. Younger stars like our Sun formed later from gas that had already been smoothed and settled into the galaxy's rotating plane, inheriting its circular, orderly motion. So the very way this star moves, its long, slow, elliptical journey, tells us it is a relic from a time before the Milky Way found its current shape. Over the past 13 billion years, it has completed this grand, looping voyage dozens of times. Each orbit, it has silently witnessed the galaxy's gradual evolution. It was present as vast clouds of gas collapsed to form the first globular clusters. It soared above the scene as the majestic spiral arms slowly wound themselves into existence. It has flown through regions of space that were once empty but are now illuminated by stellar nurseries it helped seed with its own faint chemical enrichment. Its motion is a historical document written in gravity. By tracing its precise path backward through time using the laws of physics, astronomers can even attempt to locate its original birthplace within the primordial Milky Way, the long-vanished cluster or cloud where it first ignited. Its journey is not just through space but through the entire history of our galactic home, a perpetual monument to the era when everything was just beginning. This star's profound age forces us to confront a deeper question. Why does any of this matter beyond the pages of an astronomy journal? The answer is that HD 140283 is not merely a distant curiosity, it is a fundamental laboratory. Its existence tests the very laws of physics across scales we can barely comprehend. The nuclear fusion equations that describe how it burns hydrogen in its core are the same principles that govern potential clean energy here on Earth. The models of convection and element diffusion within its churning interior refine our understanding of fluid dynamics and atomic behavior under extreme conditions. By studying this single point of light, we are stress testing our knowledge of how matter and energy behave across 13.7 billion years. It turns abstract theory into a concrete, observable benchmark. If our models cannot accurately account for this one ancient star, then our entire understanding of how stars live and die, and by extension how galaxies evolve, rests on shaky ground. This star grounds the epic narrative of cosmic history in something we can actually point to and measure. It transforms the Big Bang from a theoretical concept into a documented event with surviving witnesses. That is a staggering scientific achievement, but its impact reaches far beyond the equations. This star serves as a profound mirror for our own existence. Its light, which began its journey when Earth was not even a thought in the cosmos, now falls on our telescopes and our eyes. That connection collapses an impossible span of time into a single moment of perception. It forces a perspective that is both humbling and exhilarating. All of human civilization, every empire, every discovery, every life lived, has occurred in less than a blink of this star's long life. Our entire species is a very recent footnote in a story that began before our planet existed. This is not a message of insignificance, but one of breathtaking context. We are the part of the universe that has become conscious, that can look back and trace its own lineage to the first stars. We are the universe understanding itself. The Methuselah star, therefore, answers to the deepest strands of human curiosity, the drive to know where we came from and how we fit into the grand tapestry of reality. It reminds us that our home is not just this planet or this solar system, but a vast, ancient, and beautifully evolving cosmos that we are only just beginning to learn how to read. The quest to understand our cosmic origins is accelerating, driven by a new generation of telescopes designed to see further and sharper than ever before. While the story of the Methuselah star has been clarified, it is far from finished because our tools are about to become exponentially more powerful. The next chapter will be written by observatories that will treat stars like HD 140283 not as faint mysteries but as open books. Leading this charge is the James Webb Space Telescope. Unlike Hubble, which primarily sees invisible and ultraviolet light, Webb is an infrared specialist. This is a game-changer for studying the earliest epochs. The light from the first stars and galaxies has been stretched by the expansion of the universe over billions of years, shifting it into the infrared part of the spectrum. Webb is built to capture that stretched light, allowing it to peer directly back to the era when the first generations of stars were igniting. While it may not observe our specific Methuselah star in detail, its mission is to study the environment that created it. Webb will analyze the chemical fingerprints of the most distant galaxies we can see, galaxies that are themselves made from the light of those first stellar generations. By doing so, it will provide the crucial context for stars like HD 140283, telling us what the average conditions were like in the cosmic nurseries of the early universe. It will help us understand whether the star's specific chemical pattern is typical or an outlier, refining our models of how those first supernovae polluted the primordial gas. On the ground, an even more direct examination is being prepared. In the high deserts of Chile, construction is underway on the Extremely Large Telescope, or ELT. As its name implies, this is a behemoth. Its main mirror will measure an astonishing 39 meters across, gathering over 10 times more light than today's largest optical telescopes. For a faint, ancient star like our subject, this is like switching from a candle to a floodlight. The ELT will not just collect more light, it will slice that light into spectra of unimaginable resolution. Think of the current spectrum of HD 140283 as a paragraph of text. The ELT's spectrum will be that same paragraph, but every letter will be clearly defined with spaces between them, and even the subtle ink variations on the page visible. This resolution will allow astronomers to detect trace elements present in amounts so tiny they are currently invisible. It will measure isotopic ratios, the different forms of the same element, which act as a precise thermometer and chronometer for the star's interior processes. With this data, scientists can virtually eliminate the remaining uncertainties in the stellar models. They will pin down the exact rates of convection and diffusion, finally solving the subtle physics that currently leave that 700 million year margin of error. The ELT could deliver an age for the Methuselah star precise to within a few tens of millions of years, a blink in its long life. What secrets might these new eyes uncover? The potential revelations are profound. By obtaining pristine spectra of dozens more ancient halo stars, we could finally classify the different types of first-generation supernova. Did they all explode with the same violence, or were there different populations of those primordial giants? We might find stars even more metal-poor than the current record holders, objects that are truly second-generation, formed from the ashes of a single specific supernova. Such a star would be a direct snapshot of one individual from that lost first generation. Furthermore, these precise observations could reveal subtle anomalies, chemical abundances that do not quite match our predictions even with refined models. Such discrepancies are not failures, they are gold. They could point to physics beyond our current standard models, perhaps hints about the behavior of fundamental particles in the extreme densities of the early universe, or evidence for rare types of nuclear reactions in those first stars. The ancient stars of the halo are a cosmic laboratory for physics across time, and we are just now building the equipment to run the most sensitive experiments. We stand on the threshold of a new era of cosmic archaeology. The faint points of light that have witnessed the universe's entire history are about to start speaking in clear, detailed voices. The decades-long conversation with the Methuselah star, which took us from paradox to precision, is merely a prelude. The next generation of telescopes will not just listen to one elder's story. They will convene an entire council of ancient witnesses, compiling a full and definitive record of the universe's first chapters. The light that has traveled for billions of years is about to meet the technology that can finally understand it. This star, HD 140283, stands as a singular monument in the sky. It is one of the oldest known objects in our entire galaxy, a pristine relic whose light carries the chemical memory of a universe only a few 100 million years old. Its story is a masterclass in the scientific process. The initial shocking measurement that suggested it was older than the cosmos was not a failure but a catalyst. It forced a meticulous re-examination of our tools and models, a process that ultimately brought the star's timeline into perfect harmony with the universe's own. This is how science truly works, not by being right the first time, but by being relentlessly self-correcting, guided by evidence toward a clearer truth. The star's ultimate value is not in a dramatic paradox, but in its profound purity. Its atmosphere, almost devoid of heavy elements, is a direct sample of the Milky Way's building materials. It is a living fossil that offers us an unbroken link to the infant galaxy and the first unimaginable generations of stars whose explosive deaths made our own existence possible. To study this faint point of light is to conduct archaeology on a cosmic scale, reading a history written in hydrogen and helium before Earth, or the Sun, or even the galaxy's spiral arms had taken shape. A single beam of light from that ancient star has been traveling through the void for over 13 billion years to reach your eyes tonight. It is a messenger from an era before Earth, before the Sun, before the Milky Way took its spiral shape. That lonely point of light in Libra is more than a star. It is a beacon from the dawn of time itself, a testament to endurance on a scale that defies human imagination. Every war, every empire, every whispered word in all of human history has unfolded in less than a final, fleeting blink of its long, silent life. This perspective is not meant to diminish our story, but to frame it within the most majestic narrative of all. We are the part of the cosmos that has become aware, that can look back across the eons and trace our lineage to the first fires. The Methuselah star reminds us that we are not just living on a planet, we are living inside a story 13.8 billion years in the telling, and we are only just beginning to read the first chapters. So the next time you find yourself under a clear, dark sky, remember this. Every star you see is a sun with its own story, but some are elders, ancient travelers whose light is a memory of the universe's childhood. They are not just points of light, they are chronicles. Which cosmic mystery captures your imagination the most? Is it the search for other Earths, the nature of black holes, or the ultimate fate of everything? Share your thoughts in the comments below. If you want to join more journeys to the edges of space and time, be sure to subscribe.